So you got yourself a smartphone or an iPad or tablet or something. Most people do. Charging is easy. Just plug it into the USB port or into a charger and it charges. It's done. What happens if you've got multiple devices? What happens if you've got friends coming around and they all want to charge because they've got to get their photos to Instagram? Well, I'm going to show you how to make a charger that will charge multiple devices at up to 2 amps each full current simultaneously at the same time. Let's get started. So what do we need to build this awesome power supply? This is the list. An enclosure. I'm using aluminium just to try and shield any noise coming out, electrical noise, and because it looks nice and it's strong. Plastic ends so it's easy to machine. I will show you what I've done on the end here in a second. We'll talk about that next. Power supply itself. These are all various switch mode power supplies. All 5 volts. We've got a 20 amp. These, you get these on eBay very cheap. 20 amp 5 volt. You can trim it on the trim pot just here. Mains in and then voltage out. Easy. These aren't incredibly stable, but they're probably usable. I would put a few extra capacitors on the output there. This one here, I picked this up for a few dollars. Oh, there we go. 200 yen. Surplus in Akihabara, my favourite place. 5 volt out, and it is rated at 11 amps if you have forced cooling, like a fan, and 8 amps if it's just passive cooling. 8 amps is a little bit low. If you've got 4 ports, USB ports, it'll do 2 amps. But I want a little bit more than that. And having a fan can be noisy, so I might keep this one for another project. Then we have this one. This is a very, very nice power supply. It's made by TDK. It's a TDK Lambda. It's a 10 amp 5 volt. Yeah, just like the others. 10 amp 5 volt. And it's a very well made power supply. Good quality brand. Quality capacitors, quality components. It's very nice. So I'm going to use this one. That's pretty much the reason for the large enclosure. It's a long power supply. Long and thin rather than short and square. But I'd rather use this. So I'll move those out of the way. Standoffs and screws to mount the PCBs. Then we've got a way to get the power in. This is just a IEC connector. Inbuilt fuse, always a good idea. Make sure you have a fuse, whether it's inbuilt or a separate fuse holder that sits next to the plug in the back panel or something. And this is a noise filtering one, so I thought, hey, I've got a few spare, so we'll filter any noise coming in and out of the device. I have another video on the inside of this, so if you check that out in the link, you can see what goes on inside these things. Then we have a power switch, just a standard on-off switch. This one's got a LED illumination, nothing fancy. Then we have our USB ports. This is a USB hub, cheapest one I could find. Check out this link and you'll see the rundown on this. I'm going to be using this in this project, so we've got 4 switches, 4 USB ports. The rest of it's not going to go unused. That way we can turn on and off individual ports as we need to. Beautiful. Some LEDs in your choice of size and colour, just to give you an indication of what's turned on and off. These ones have blue 3mm. I don't like blue. I think it's a bit 2000s futuristic, so I'm going to go for a standard green. Some polyfuses, resettable fuses, just on the outputs. These are around about 2 amp, maybe just over 2 amp each, so we're going to use one of these for each output. Miscellaneous hookup wire and various hardware, screws and rubber feet for our enclosure. That's pretty much it. That's all we need to put this thing together. Now for putting this thing together in the way of tools, it's basically just the standard hand tools and, you know, battery drill, soldering iron, side cutters. But one thing I recommend you get is one of these. This is a nibbling tool, and it's awesome for square holes, because it's very hard to drill a square hole with a round drill bit. So what this thing does is, if you can see at the end here, if it's going to focus for me, is this bit that moves in and out. It's actually a cutting bit. You can see, kind of see the shape there. What happens is, you have your piece of material and then you put it up inside there, and when you pull the handle it takes out a notch, a little square notch. So you can drill a round hole to start with, put this through and then start notching along, and you can make a line and squares and different shapes like that. It's fantastic. It's a lot easier than getting your X-Acto and trying to cut through the plastic. This just nibbles it away. It's really, really good. Really easy to use. They do have a maximum thickness defined by the distance between the top of the jaw and the base plate here, and they're better for aluminium and plastic rather than steel. Steel can be cut with these, but not too thick. Things like the side panel of your case, your computer case, or this sort of thickness steel, this thing will just eat through it, but don't go too thick. Aluminium and plastic obviously can go thicker, but yeah, definitely worth getting something like this. Alright, let's talk about these things. These are the end caps on our enclosure, like that. Enclosure in the middle. One for the front, one for the back. So what I've done, you can see this square here, and then on the front panel I've got a whole heap of different shapes. What I actually did was I got my CAD software or my drafting software of choice, and I measured everything up, measured up the size of this panel and all the things I wanted to go in the panel, and I drew up a design. I've then printed that out at 1:1 scale, cut it out, and then stuck it on. What do we got here? This one on the back panel is the cutout for this. So if I cut out that line, I can just stick that through and it'll fit perfectly. On the front here, we got the power switch and that USB hub. This one here will go in, and then a row of dots here for the LEDs, and that will just fit straight in perfectly. What I do is, once I cut the paper out, I use just a glue stick, like water-based glue, to stick that on. Once I've cut it all out, I can peel it off and wash it under water, and it will all come off clean and it will look perfectly in line and beautiful. A lot easier than trying to draw it on there by hand and get things lined up. It's going to be perfectly in line, and it's a lot easier to get things just nicely positioned. You can also do the design on the computer and see what it's going to look like before you go and draw it all out. So you can get things just like visually balanced on the front panel. Alright, so there's our rear panel done. I ended up finding that I couldn't use this awesome nibbler because the nibbling thickness capacity was smaller than the thickness of the plastic, which kind of sucked a bit, but I ended up just drilling a series of 1mm holes all around the edge of my cutout, just inside, and then I used flush cutters to nibble it out, and then I used my X-Acto and some files, small files, just to get it just the right shape so it's nice and snug. So that's that done. Just washed off the paper with the with some water, and it just came straight off and it's all clean because I used the glue stick, the water-based glue. So that's one side done. Now what we have to do is the other side. This one's going to be a bit more complex, but hey, not too difficult. Alright, so here's the front panel finished. We've got a main power switch and then the individual switches and LEDs for the USB ports. Pretty simple. Power on and off, individual power for each USB port on and off. That way you can turn off power to a certain device but keep the other ones on, you know, charge one device but turn another thing off. On the back here we've got our PCB that was from that USB hub. I've reused that chiefly because the switches and the USB ports have already been drilled, and you know, it makes connecting things easier rather than just going complete dead bug. It means I can you know, have a bit of mechanical strength to things. Then we've got our main bus bar across here. I put this in because I wasn't too confident on how well the thin traces were going to carry current. Each USB port could be delivering up to 2.5 amps, so some of these traces went all the way around and weaved in and out to try and stop having to have any jumpers, because that's extra production cost. So I thought, we'll do away with that and have a nice bus bar. It's just some of this wire which I stripped and tinned. I also come in through the center, not the end, because if I come in the end, this one here, like to say it's this end, this one here will carry the most current, because it could be up to 2.5 amps per outlet. So there's 2.5, 2.5, 2.5. That's 7.5 amps through this one side. But if I come in through the middle, the most is going to pull this from the middle point here to here is 5 amps, because it's 2 on one side, 2 on the other, 2.5 amps per point. Half this side, half that side. It just spreads the load a bit better. I've done the same with the negative. You see, I didn't put a bus bar for the negative. The reason is, if I can get close enough, you can see the larger solder points. There's a 1, 2, 3, 4, all the way along. That's actually for the metal of the case of the plugs. So the actual case of each plug is acting as the bus bar. A lot of metal, so it's going to be fine. I've got the poly switches here, one for each outlet. There's around about 2 and a bit amps. So if you're pulling 2.5, eventually it might trip. But they're well sized, and I've made them stick out so that we can get a bit of air ventilation, so they cool down and stay working correctly. Then over this side we've got these 2 wires. These are wired directly to the 5 volts coming out of the power supply, and they go to this green LED here. So whenever the PSU, the switch mode power supply, is outputting 5 volts, the green LED here will light up just like a power light. These ones here are wired to the switches, so when the switch turns on, then the corresponding LED comes on. Pretty easy stuff. Pretty straightforward. One other thing regarding the power switch, the hole here is 20mm, so how do you cut a really neat, nice round hole that's a tight fit without filing or using a hole saw which can rip a bit? Well, there's this really good drill bit called a step drill, and what it does is, you see the steps, you drill in, and as you go further in, it obviously, as you can see, makes the hole bigger and bigger. This is a metric, so it steps up in 2mm increments. I've got another one that's a thinner one which goes up in 1mm increments. They're really good for plastic and aluminium and thin steel. They give you a really nice smooth circle, and they don't rip the material like a hole saw sometimes can if it wobbles a bit and you end up with a hole that's kind of ragged on the edges. Yeah, really good for drilling panel holes. There is one more thing we have to do with this before we put it together, and that's set the data pins to tell our devices that we can actually pull a lot of current. Otherwise they're going to just charge at low rate, and there's no point to having this device at all. So for Android and other devices, all we have to do is just put a solder blob on the data pins, which is the 2 innermost pins of each set of 4. So I'm going to do that with these 2, and then these 2 I'm going to set them for Apple, Apple devices like iPods and iPads and stuff. For that, because Apple, we need to make a resistor network. So you pause now and I'll put the schematic on the screen. Right, so I've got the power supply here mounted. All I did was just lay the power supply in the enclosure, use a Sharpie to poke through the mounting holes onto the enclosure itself. Drilled a few holes. I drilled 3.5mm holes because I'm using 3mm standoffs, the size of the screw, M3s. That extra 5mm just gives me a little bit of play, just so I can get things lined up without putting too much stress on the circuit board, because you can never drill perfectly aligned, so a little bit of play is good. So that's all in there. You'll notice as well that I've got this piece of plastic. I put that in there because I wanted a bit of extra isolation between the mains voltage on this end of the board and the metal case. It's all going to be earthed, this metal case, and it's actually earthed through this leg here, but I figured it's almost free, so it's not going to hurt to have the extra isolation. I'm actually going to end up putting a star washer on this single screw. The reason for that is because the earth pin, which is this pin just here on the right there, that's got the trace coming around, so this whole heatsink is earth. You can actually see the brown sort of colour. That's the earth trace, and it goes past this screw, this mounting screw. So that means that it earths down through here to the case. The star washer, when you tighten up the nut, or the bolt, sorry, that will cut through the lacquer and cut through the oxide layer on the aluminium to give a good strong earth. You don't need to do it on the other ones, just on the earth side. So I'll put that on a bit later, and then once we've wired up we can just test from a bit of bare aluminium to the earth pin on the socket, on the IEC socket, and then we can make sure we've got a good earth to make sure that's all safe. So that's the power supply mounted. Next, so I've made all my connections and we're pretty much ready to power it on. It's not a very complex setup, but I'll run through and show you what I've done. So basically we've got an earth connected to here, which comes straight back and is soldered onto the earth lug on our IEC connector. I soldered the other two. I was kind of deciding whether I should use crimp lugs and solder them on or solder them. I thought, I'm not going to take this thing apart very often, so I may as well solder them and get a really good robust connection. Heat shrink on there so that we're nice and safe. Cable ties to stop it flapping around in the breeze, and we come to the connector. Now I didn't have the crimp for these little pins in here, so what I did was I used my pointy nose pliers and just carefully crimped them over with my pliers and then soldered them. So they're definitely not going to come out. That's as strong as it can get. Then, like I said before, the earth is connected to the chassis through that screw there, and then that is going to get a star washer on that screw to dig through the oxide layer and into the bare aluminium, so our whole case is earthed. And basically what happens is the power comes through here. We've got a fuse just here, comes to the power switch. From the power switch it comes back into the power supply, and then from the power supply straight to our IEC and back out to the mains. So that's the main side of things. Over here you'll see two sets of wires. Originally I only had one, and I was talking about that bus bar system. I ended up cutting that in half because I thought I didn't want to overload any of the pins here. I want to keep the load spread as much as I can. Seems like I could be pulling up to 10 amps. I'd rather have 5 amps through each pin rather than 10 amps just through one set. So I took that half that bus bar out just here, and one set of wires comes to one side and the ground, and the other set of wires comes to the other side and the ground. On the PCB they're connected together. It's not a split rail or a dual rail power supply. So I could have left the bar in the middle, but it was easy just to take it out and solder them separately. No big deal. Then we've got the resistors down the bottom and our jumpers to set Apple and Android, the charging rates. Switches like I mentioned before, and we're all good. Another modification I did make, you can see resistors 1, 2, 3 and 4. The carbon traces that were there were around about 120 to 150 ohms, and they were set for the blue LEDs. When I had the green LEDs, they were so bright they pretty much blasted me into orbit every time I turned these switches on. So I went and put 630 or 680 ohm resistors in just to make these lights not so bright, because if it's sitting on my desk and I got it turned on, I don't want to be blinded by the lights. Just a subtle indicator that the thing's actually on. So the 680 or 630 ohms, whatever I used, comes to about 5 milliamps running these LEDs, and that's perfect. That's plenty bright. Your eye is very sensitive to green, so it doesn't have to be so bright. It kind of matches the brightness of the switch as well. So that's pretty much our power supply. So let's plug it in and see what we're getting. Alright, so I've got the thing set up. We've got a USB cable here coming through to my multimeter, set on the volts range, ISC cable, so we can turn it on and turn on our output. 5.151 volts. I've got a trimmer here, which I've trimmed it. The USB spec is 5 volts nominal, with a maximum of 5.25 volts. So I've gone up just a little bit, just to 5.15. The reason I did that was just in case we've got a bit of voltage drop in our cables, or things load up and you got a bit of resistance here and there, it won't go below 5 volts. Things like Raspberry Pis can be a bit sensitive to under voltage, so a little bit above, still within the spec, and that way we know we're going to always have at least 5 volts at our output. I also made sure to measure it on the actual output and not, you know, from the output of the power supply, because if I do that, then we've got to take into account the resistance of the wires and our polyfuses and whatnot. So taking the voltage from the other side of the polyfuses and our wiring, which can all add up with a bit of resistance, gives you a more accurate reading as to the actual output. On the pot as well, the trimmer pot, once I got it perfectly set, I put a bit of nail polish on the pot, just where the sliding parts, you know, just across, just like a bit of an anti-tamper sort of thing, so it won't vibrate, you know, to a different value, because it's very sensitive. So a small bump could put it out by, you know, a tenth of a volt, or you know, 0.2 of a volt or something. And that could be not so good if it goes the wrong way. So that little bit of nail polish will just help to hold the trim pot, so it won't alter the voltage. So that's pretty much it. It all comes down to just putting the lid on and seeing if it charges. So let's do that, and I'll plug my phone in and see what happens. Alright, so I've got my setup here. We've got the fluke plugged in just like it was before, just to monitor the exact voltage coming out. I've got this little volt amp meter, little blue thing. They're very common, not incredibly accurate, but hey, it will give us a rough idea. And I've got an app on my phone running called Ampere, which tells me how much I'm drawing or charging, you know, how much power it's using or how much power it's sucking from the charger. At the moment we're measuring, it'll come up to about negative 450 milliamps, which is, there we go, 450 milliamps. That's pretty much what the phone's using just to turn the display on. So let's turn this on. So I'll turn on the fluke first, 5.15 exactly, nice. And if we turn on the phone, now it's measuring, gone blue because it's charging. Give it just a second. 1200 milliamps. So 1.2 amps. That's about right for these phones when the screen's running, because the screen takes a bit of the current and it's got a maximum power that will draw. So if we turn the screen off, maybe that'll go up. So at the moment this blue one here is saying 1.15 ish, 1.18, so it is actually pretty accurate, 1.17. So let's turn the screen off. Yeah, there we go, 1.78. So it's charging at about 1.8 amps, which is what the specs are on the phone. The screen is off, it charges at 1.8. This is a little bit under, but if we turn the screen on, it's gone down to 1.2 amps, and this is saying just under 1.2 amps. So it looks like we're able to charge at the full charging rate, which is pretty good. So let's see what it does in a normal USB port. I've only made the first one, the one I've got the fluke plugged into, to be an Apple specific. I ran out of resistors, so I'm going to have to do that later. But our second one is actually just an open USB. It's power with no data pins connected. So let's plug this in and see what it says. So measuring, give it just a sec. This is saying 0.44 amps, so just under half an amp. Yep, 450 milliamps. So that's about correct for a just a USB port that has no resistors or no setup on the data pins. The phone doesn't know how much it can draw, so it goes to the minimum amount allowed by the USB spec without any negotiation capabilities. So that's correct. The only thing left to do is a data plate, which is kind of important, I think. You know, output, input ratings, that sort of thing, the type of fuse to use in the IEC socket. Also, because this Lambda, TDK Lambda power supply is only 100 volt. It's something from 85 to 125 volts or something. So you can't plug this one into a 240 or 230 volt outlet. It's no problem for me because I've been living in Japan and we've only got 100 volts. I'm not looking at moving this thing around to different countries, but it's always a good idea just to put it on so in the future someone doesn't inadvertently plug it in and let all the smoke out. So I'll show you in another video how to make nice data plates, and we'll stick it onto here. So yeah, there we go. All done. Ready to power any 5 volt USB devices. See you next time.